This is going to be the start of our energy unit, and energy is one of the most important units we do. There's really two basic ways to do problems. One is to think of forces, we do F net equals ma, and the other way is thinking about conservation of energy. And sometimes conservation of energy is the best and easiest way to get through a problem. So we're going to start out by talking about energy is conserved. In chemistry, they may have said something like energy cannot be created or destroyed. Okay. So what that's going to mean in terms of how we're going to solve problems is that the total energy at one point is going to equal the total energy at another point. However, energy can change forms. Okay, if you think the light's lighting up a room, you have electrical energy being converted into heat and light energy. The electrical energy originally came, say, from a nuclear power plant where it took nuclear energy, turned it into heat energy to create steam, to spin turbines, which is mechanical energy. Then those turbines convert the mechanical energy into electrical energy, and then it gets transmitted to your light switch, turn it into heat. So there's a lot of different transitions, but the energy can't be created or destroyed. There's two main types of energy we're going to deal with. First one's potential energy, and you can think of potential energy as stored energy. Now, there's going to be various types of potential energy, two of which we're going to use, but you need to know that there's other options as well. One is gravitational potential energy. We're going to use the symbol PE for that, and that just depends on height. Okay, as I lift something higher and higher and higher, I'm giving it more potential energy, and then if I drop it, the higher the height I drop it from, the more kinetic energy it's going to gain as it falls, the more work it can do when it hits the ground. Another type is elastic potential energy. And that's the type of energy stored in springs. Okay, or something like a diving board. Okay, as you jump down to the diving board flexes. As it's flexed, it's storing energy, and then it straightens again, and that energy gets released. And the symbol we're going to use for that is PES, for potential energy in a spring. But it doesn't have to be a spring. It could be like a diving board, a trampoline, or whatever. Now, those two we're going to use in our problem. We probably won't use these, but you need to know that there are other forms, like chemical potential energy, that's stored in bonds. So chemistry had to deal with that. But if you think this is how we get our energy when we eat food, we break apart those bonds, and that gives us our energy. And there are many, many other forms, okay? But mostly we're going to use gravitational and some elastic potential energy. Kinetic energy, we know, is energy of motion. And it depends on velocity. The faster something's going, the greater kinetic energy. And we're going to deal with calculating both types, gravitational and kinetic, in a little bit. But for right now, we're going to just talk about qualitative problems, where we just have to see what's going on. So we have an example. A roller coaster starts at rest at point A, and it's going to go down the first hill through point B, then around the loop. It's going to hit point C at the top, and then finish off at point B. And we want to show a diagram kind of showing the kinetic and potential and total energies at each of the labeled positions. So at point A, I know its velocity is 0. It says it starts from rest. So it has no kinetic energy. But it's going to have potential energy because it has this height here. So I'm going to give it, quite a bit of potential energy. This is the highest point on the roller coaster, so it's going to have the most potential energy there. And I'm going to divide this up just to get some feel for how big it is. I divide it up into 4 sections. So the potential energy is 4 units high. Now we just said the kinetic energy is 0, so we're going to put a little mark at 0 for the kinetic energy. Then the total, I would just add those up, and the total is going to be 4 high. Okay? Now, the fact that energy is conserved is going to let me know that the total energy is always going to be 4 high. So at every point, I can now draw the total energy in. If I was being really careful, I'd make those the same height. That's not too bad. Okay, now at point B, I get down here at the bottom. Here the height is 0, so the potential energy is 0. So I know that we have no potential energy. So how big does the kinetic energy have to be? Well, I know the total has to be 4 units high. I have no potential. Therefore, the kinetic has to be 4 high. Because the potential plus the kinetic has to add to the total. Now, point C. Now, you'll notice over here I said that point C is half as high as the whole thing. So if we had 4 potential energy over here at A, if we're half as high, we might assume that we're going to have about half as much potential energy. So I'll split that up like that. Now again, my total is 4. I have 2 in potential energy. How much kinetic do I have to have? And it turns out I'm going to have 2. And then at the last position, D, now the height is 1/4 as high. I think the potential energy is going to be about 1/4 of the total then. And then if that's 1 high, the kinetic energy has to be 3 high to give me a total of 4. So that is a way of diagramming these. Now, top of the next page, we have another example. You draw a bow back, and then the arrow is fired. Okay, and it's going to follow this path. And we want to show the PE, the KE, and this time there's spring potential energy and the total energy. Now, at point A is when the bow is pulled back. So we're going to write PE here. We're going to write PES, maybe. We're going to write KE, and we're going to write total. Okay? Now, if I think about this, the height here is 0, so there's no gravitational potential energy. The velocity is 0 when I'm just holding up the bow drawn, so the kinetic energy is going to be 0. So I know these two are both 0. Well, where's the energy? It's all in that flex string. Okay? And you're holding it, and that's potential energy. So I might go ahead and give it some units of potential energy, maybe 5. Okay? And that means my total energy is going to be 5. Okay. All right. Now, at point B, we just let go of the string, and at that moment, the arrow is flying out of the string. So now what type of energy is it? Well, it still hasn't gone up in the air yet, so the height is 0. There's no more spring energy because the bow has been released, so the PES is going to be 0. So we'll make our little chart. We got PE, PES, we got KE, and we got total. We just said the height is 0, so potential energy is going to be 0. PES is 0 because the bow is no longer pulled back. I know that the total energy has to be 5 high. So how high does the KE have to be? Well, all of the energy now is kinetic energy, so the KE has to be 5 tall as well. Okay, next one. Part C. It is at the top. Now, you have to be a little bit careful because we look at that, that's the highest point. Okay, so we know the PE is a maximum there. And in our heads, a lot of times we say kinetic energy is going to be 0. But that's not the case. It still has some velocity. So therefore, it will have some kinetic energy. So I can't make it 0. However, that's the smallest. And the spring potential energy is gone at that point. So because the bow is still not drawn back, we have PE, PES, KE, and D total. All right. Now, we just said that the PES is going to be 0 because the string is not pulled back on the bow. It has some kinetic energy, but probably not a whole lot. So I might represent that as 1. Okay. I know my total energy is 5. Okay. So then the potential energy has to be, in this case, it would be 4. Now we're just making these numbers up. It may not be exactly right. Okay, but we're just trying to get a feel for what's happening. So as the arrow flies upward, the potential energy goes up, and on the way up it slows down, so the kinetic energy goes down. But the sum of those potential and kinetic energy has to be the same every time. And then our last point, point D, okay, is back down towards the ground. All right, we will have a height of 0 here. Okay, the string has long since been released, so we have no potential energy. All right, so if we do PE, we have PES, we have KE, and we have total energy. We've just said we have no potential energy because of height 0. We have no PES because the string is not taut anymore. We know we have 5 for total, and therefore the KE has to be 5. So that is one way to look at these problems, just doing qualitative analysis. And it's just so you're seeing where is the potential energy highest, where is the kinetic energy highest, when is potential turning into kinetic, and so on.